Hello everyone. Welcome to ILTA Physics online lecture. Today we are going to solve some problems regarding Newton's second law of motion. This law is also known as the law of acceleration, and it is very well known to us as the formula F equals ma. The following image shows the relationship between the magnitude of the force applied to an object's motion and the change in its velocity, which is the acceleration. When the same amount of force is applied, it is easy to understand that a light object like a basketball will move with greater acceleration, while a massive object like a car will show much smaller acceleration. In these Newton's second law problems, the most critical quantity is the change in velocity, which is acceleration. This is because acceleration acts as a very important bridge that connects kinematics and kinetics. The problems we will cover today are basic types where we use acceleration to link kinematic equations with Newton's second law. First, let's briefly summarize Newton's second law. Newton's second law explains the relationship between the force applied to an object and the resulting acceleration. Dynamics, the field of physics that deals with the motion of objects, includes both kinematics and kinetics. Kinetics is the physical analysis of force, which is the cause of motion, while kinematics is the field interested in the phenomenon of the motion itself, such as position, velocity, and acceleration, regardless of what caused the object to move. Since I have fully explained the detailed descriptions in my theory lecture, those who need the basics should definitely listen to the theory lecture first before coming back to these practice problems. We explain Newton's second law experimentally. Acceleration is proportional to the applied force and inversely proportional to the mass of the object. Also, the direction of acceleration is the same as the direction of the applied force. Expressing this as a quantitative formula gives us the familiar F equals ma. If multiple forces act on a single object, we can represent the vector sum of those forces, which is called the net force. In actual problems, we calculate changes in velocity or position by mixing the analysis of forces from kinetics with the constant acceleration formulas from kinematics that we learned previously. Therefore, it is a good idea to refresh your memory on those kinematic formulas below once more. Problem number 25 describes a 55-kilogram skater who is running at 3.5 meters per second and slowed down to 2.9 meters per second over 5 seconds. It asks what the kinetic friction acting on the skater was. The first half of the problem provides kinematic information about velocity and time. And the question asks for the friction force, which is a kinetic concept. This is a typical basic problem that can be solved with Newton's second law. Before we start calculating, we must determine the coordinate system and the origin. Since this is a simple motion, let's assume horizontal motion and set the right side as the positive direction, and the object's initial position as the origin. Even though this problem is very simple, please get into the habit of setting a coordinate system before solving any problem. As shown in the image, the velocity decreased from 3.5 meters per second to 2.9 meters per second over 5 seconds. So according to the definition of acceleration, the acceleration is negative 0.12 meters per second squared. One thing to be careful of here is that since we set the direction of motion to the right as positive, and the speed is decreasing, the direction of acceleration is to the left, which is negative, opposite to the motion. The cause that created this acceleration is the kinetic friction. According to Newton's second law, F equals ma, we can find the friction force by multiplying the mass and the acceleration. The calculation result shows the friction force is also negative 6.6 newtons, which means the friction acts in a direction that opposes the motion. Actually, because this problem was so simple, we could easily solve it using just the definition of acceleration and the F equals m a formula. However, if we analyze this motion a bit further, you need the skill to accurately analyze all forces acting on the skater using a free body diagram, like the one in the image on the right. For now, let's just understand that the kinetic friction we found acts opposite to the direction of motion, meaning it has a negative value, and move on. In the next section, we will practice solving related two-dimensional motions using free body diagrams. Problem number 26 is a description of the motion of the IKARO spacecraft launched by Japan in 2010. As shown in the image below, the IKARO spacecraft gets energy from sunlight and uses it as power for the spacecraft without separate fuel. When a force of 1.12 millinewtons is applied to a 290 kilogram spacecraft, it asks for the change in velocity after 6 months. Again, let's first set the coordinate system and the origin. Generally, we will consider the right side as the positive direction and the initial position as the origin. Since the force F and mass m are given, we use the F equals ma equation to find the acceleration of the spacecraft. Since the applied force is very small, the acceleration will also have a very small value. Now, according to the kinematic formula, the change in velocity, delta v, is acceleration times time. We need to convert the time of 6 months into seconds. A tip is to calculate 6 months as exactly half of a year. If you calculate this, the change in velocity after 6 months is about 61 meters per second. Even though it is a very small acceleration, you can see that a significant change in speed occurs if the force is applied steadily for 6 months. The problems we solved today were the most basic types of applying Newton's second law. Even for simple problems, please make it a habit to set the coordinate system first and think about the direction of motion. That way, you can accurately grasp the physical meaning of the calculated results, whether they are positive or negative. That's it for today's lecture. Great job today. See you next time.